Hello everyone, welcome to SAIMEDHA Koti Hyderabad. Let us solve the questions of transformer which were given in the Tspsc-Aee 2023 paper. So let's read the question. A question is, in a single phase transformer supplied from the constant voltage, magnitude of the load current kept constant while power factor is a vary under this condition. Option 1, maximum efficiency of the transformer at unit power factor. Power factor where maximum efficiency occur depends on the leakage inductance value. The maximum efficiency occurs at a power factor 0.5 lead and maximum efficiency occurs at power factor 0.5 lagging. Okay, we know initially efficiency of the transformer, that is a percentage the efficiency of the transformer, percentage efficiency of transformer. What is the formula to find out percentage efficiency of the transformer? So under at full load condition, okay, at full load the condition equal to output power is I2 cos theta 2 the divided by output power I2 cos theta 2, okay, plus iron losses Wi and the full load copper losses I2 square R02, so multiplied by 100. This is the general formula to find out the efficiency of the transformer. So from this formula, so we conclude that the percentage efficiency of the transformer is a double valued function. That means depends on the two factors, percentage efficiency of the transformer, a function of the two variables. One is the load current I2 and power factor angle theta 2 here. So in this question clearly mentioned that load current is a constant and power factor is a varied. So this is a I2 is a constant, okay, constant value, and this one is a variable, power factor is a variable. So by keeping the load current constant, power factor is a varied, and what is the condition to get the maximum efficiency of the transformer? So now in this case, to get maximum condition, what we have to do, the maximum condition. So the differentiation of the efficiency with respect to the variable power factor, so that is the power factor angle, and make it equal to the 0. So this is the condition to get the maximum efficiency. But in this case, I2 is treated as a constant. Okay, it is mentioned. So it is a double valued function. To get the maximum efficiency, what we have to do? So we keep the one quantity as a constant, differentiate the efficiency with respect to the another quantity and make equal to the 0. So by solving this equation, okay, by solving, so we get, okay, this we get the cos theta 2 the is equal to the 1. So it is nothing but, okay, this one is a the unity power factors. Okay, this one is power factors here. So that what is the answer for this question? By keeping the load current constant and power factor is the only varied, the maximum efficiency occurs at unity power factors. So that option 1 is a correct for this question. Okay, got it? Let us solve another question. The question is Buchholz relay commonly used for the protection of the which of the following? Option 1 bus bars, option generators, option 3 transformers, and option 4 is the transmission line. The Buchholz relay is used to protection of the transformer from the internal faults. So that option 3 is the correct for this question. Okay. Now let us solve another question. In a transformer, the load current is kept constant while the power factor is a varied. So what is the given in this question? The load current I2 is a constant. Okay, this I2 is a constant and power factor is a varied. Okay, this is the power factor varied. And what is the condition to get the zero voltage regulation? Okay, zero condition, zero voltage regulation will be observed at unity power factor independent of the load power factor. Load power factor is a leading, load power factor is a lagging. So now we need to find out this one is a zero voltage regulation. Okay, so we know from this voltage regulation curve. So let us take, so this is the percentage voltage regulation of the transformer, and assume this is the unity power factors, and it is the lagging power factor side. Okay, that is the ZPF lag, and it is a zero power factor lead, ZPF lead. So power factors values we have given here. Suppose it is a unity power factor, this will become 0.8, 0.6, 0.4, 0.2 and 0 power factors. Now similarly 0.8, 0.4, 0.4 and 0.2 and 0 power factors. So this is a the zero voltage regulation of, okay, this zero voltage. What is the regulation at unity power factor? This value is equal to percentage R. So now this is exactly the approximated curve. So now this is a zero voltage regulation. Okay, zero the voltage regulation value. So this voltage regulation occurs at the leading power factor side. Okay, so that what is the answer here? The load power factor is a leading. Okay, zero voltage regulation of the transformer occurs at the leading power factor, whereas maximum voltage regulation occurs at the lagging power factor loads. Okay, got it? Let us discuss this question. Which of the following statements are entirely true regarding eddy current losses? Eddy current loss can be minimized by thin laminated core. Eddy current loss proportional to the flux frequency. And another option, eddy current loss can be minimized by using material which have low hysteresis coefficient, and eddy current loss is proportional to the square of the flux frequency. Direction of the eddy current can be found by Lenz's law. Eddy current loss is proportional to the square of the flux frequency, and eddy current loss can be minimized by using the material which has the hysteresis coefficient, low hysteresis coefficient, and eddy current loss is proportional to the flux frequency. So here always eddy current loss, okay, this is the eddy current losses, the directly proportional to the square of the frequency, the when B maximum is constant. Okay, B maximum is a constant. So this is the eddy current loss. And next one, eddy current losses can be minimized by using the material which has a low hysteresis. No, it is not at all correct. So now, but eddy current means the current flows in the core. That is I square R current in the core. So this direction of the current can be obtained by using the Lenz's law. So direction of the eddy current can be found by using the Lenz's law, and eddy current is directly proportional to the square of the flux frequency. So this is the eddy current losses. Answer, eddy current losses is directly proportional to the square of the frequency, and direction of the eddy current can be found by using the Lenz's law. Okay, so that option 3 is the correct for this question. Okay. Next, let us solve another question. The question is maximum efficiency of the single phase transformer operating at unity power factor is found to be 90% under full load condition. The efficiency at the off load at the same power factor would be, and options here, option 1 is a 88.3%, option the B is a 90%, option C is a 84.5%, and option 4 is a 87.8%. So we know the formula to find out the maximum efficiency of the transformer. So now this one is a percentage. Okay, what is the given data here? Given data in this question, the maximum efficiency. Okay, this maximum efficiency, percentage maximum efficiency equal to the 90%. Okay, at unity power factor. Okay, and the full load. So and full load condition. Now, what is the required percentage efficiency of the transformer? Okay, at percentage at off load and the same power factors. That means percentage efficiency of the transformer at off full load condition, off full load and unity power factor load. So this is the requirement. Okay. Now, how do we solve this question? We know that percentage efficiency, percentage maximum efficiency of the transformer. So that is equal to, okay, S into, so this one is the S into cos theta 2, the divided by the S into cos theta 2, okay, plus 2 times of the iron losses multiplied by 100. Okay, this is the maximum efficiency formula. Now, where S is nothing but, okay, where the S is a VA rating of the transformer. VA rating of, okay, transformer we have considered. Consider that S is the VA rating of the transformer. So, in this case, given here 90% of efficiency at full load and the full load unity power factor and full load condition. How do we answer this question? See, initially the S is equal to 0. Suppose 90% means 0.9. The S is the S cos theta is equal to 1 and S into 1 the plus times of the iron losses. Okay, 2 times of iron. Now simplify this. Okay, this one is a 2 times of iron loss is equal to S by 0.9. Okay, 0.9 minus the S. Okay, this one is the full load copper losses, 2 times of iron losses. Now let us find out iron losses. What about this value? So we can solve this one. 1 divided by 0.9. Okay, minus 1. Okay, this value is equal to 0.11 S. Okay, this is that. And next one, what about the iron losses? Iron losses equal to, so this say divide 0.111, okay, S divided by 2. So it is equal to 0.0 the 555 S. Okay, this is the iron losses of the transformers. Now, the maximum efficiency, okay, occurs. We know that the maximum efficiency the occurs at, okay, this occurs when the copper losses equal to iron losses. So that is equal to, copper loss equal to iron loss means 0.055, okay, 5 S. Okay, where S is the VA rating of the transformers. Now after getting this copper losses and iron losses, so we need to find out the efficiency of the transformers. How do we get the efficiency? Generalized formula to find out efficiency. The percentage efficiency of the transformer, so that is equal to S into the cos theta 2, okay, plus the S into cos theta 2, the plus I, this one is a the S into cos X into, okay, suppose X is the full load copper loss. So X into S cos theta 2, the X square, okay, full load copper losses, okay, plus iron losses multiplied by 100, where X is a fraction of the load. Now we require the percentage efficiency of the transformer. Percentage efficiency of transformer the at half full load and, okay, unity power factors. Okay, unity power factor condition. So now this value is equal to half full load means 1 by 2. Okay, 1 by 2. Yes, the cos theta 2. The cos theta is also equal to. So this value is a the 1. So now we have taken 1 directly. So now 1 by 2, okay, S into 1, the plus 1 square, okay, that's sorry, 1 by 2 square, 1 by 2 square into the full load copper losses is equal to, so 0.055, okay, 5 S, the plus iron losses are is equal to 0.055, okay, S, okay, 55 S multiplied by 100. So where S is a common here, suppose here also S and there also S and in this term also S. So that what will happen? So it is a 0.5. Okay, s will be cancelled out. So remaining terms here 0.5. The place, okay, this one is the 0.5, the into 0.055, okay, 55, plus, okay, 0.055, okay, multiplied by 100. Now calculate the percentage efficiency of the transformer. So this percentage efficiency you can calculate 0.5, 0.5. Yes. Okay, this value will become 97. Okay, 815%. The answer for this question is a 97.8%. So let us verify the options. Option 1 is given 88.3%. Option 2 is the 90%. Option 3 is the 84.5%. And option 4 is the 87.8%. Now see, the 87.81% is the right answer. So that answer 4 is the correct for this question. Okay, got it? Now another question. The question is, if PE and pH denote the eddy current loss and hysteresis loss, the magnetic core operating with the alternating flux density waveform frequency f, then the PE and pH both are proportional to the square of the frequency. The total loss is proportional to the frequency, and PE is a proportional to the frequency. H is a proportional to the square of the frequency, and P is a proportional to the F square, and pH is a directly proportional to the F. Now, in how do we answer this question? See, so when B maximum is constant, when the maximum flux density of the transformer core is constant, the hysteresis loss directly proportional to the frequency, whereas eddy current loss directly proportional to the square of the frequency. Okay, now let's verify. Eddy current loss directly proportional to square of the frequency. Option 4, eddy current loss directly proportional to the square of the frequency, and hysteresis loss directly proportional to the frequency. So that option 4 is the correct for this question. Okay. Next, one other question. This question belongs to the concept of the parallel operation of the two single phase transformer. So what is the question? For the parallel operation of the single phase transformer with the same voltage ratio and different kVA rating, the load is shared by these two transformers, the proportional to their kVA rating when transformers have the leakage reactance in the ohms inversely proportional to on their rating, the equal current impedance on their respective rating, and same leakage reactance in the ohm, same magnetizing current in the ohm. So in order to shade the load according to its kVA rating, so what is the requirement? Suppose the ohmic impedance of the transformer inversely proportional to kVA rating. Okay, this is a basic condition. So ohmic impedance of the transformer is a directly proportional to the inversely proportional to its kVA rating. So now it means that the impedance of the transformer A divided by impedance of the transformer B. Impedance of the transformer A, the in the ohms impedance of the transformer B is equal to the kVA rating of the transformer B divided by kVA rating of the transformer A. So this is, now let us simplify this. ZA in the ohms, the into kVA rating of the transformer A is equal to the ZB, okay, in the ohms, okay, ZB in the ohms, the into kVA rating of the transformer B. Okay, now the voltage rating of the one of the condition to connect the transformers are in parallel, that is the voltage rating of the two transformers should be the same. So that means the ZA in the ohms, okay, into kVA rating of the transformer A divided by, so now voltage of the transformer A, okay, this is equal to the here the impedance of the transformer B, the ohms, okay, kVA rating of the transformer B, okay, this one is a B, the divided by voltage rating of the transformer B. So VA square, let us take this one is a the VA square, the is a VA square one. Now in this case both VB square one. Now what is this value? The per unit impedance of the transformer A is equal to per unit impedance of the transformer B. So now what I conclude here, so this is the per unit impedance of the transformer A corresponding to the KVA rating of the transformer A, and this one is the per unit impedance of the transformer B corresponding to the KVA rating of the transformer B. So the equal per unit impedance on their respective KVA ratings, the respective KVA ratings of the two transformers, so that the which option is a suitable for this question? Option 2 is a correct for this question. Okay. Now another question, it is application point of view. Which type of the transformer is used in the AC welding? AC welding means example for this AC welding is a arc welding. So for arc welding, it is a high current is a required load side. So which type of the transformers? The step down transformer is a generally used for arc welding purpose. Now another question, which of the following characteristics an ideal transformer? Some characteristics are given: infinity core reluctance and zero stored magnetic energy and large magnetizing current and zero leakage, zero core flux. Actually, the ideal transformer characteristics point of view, what are the basic characteristics of ideal transformer? Characteristics of ideal the transformer. The first characteristics is a permeability of the core. Okay, is infinity value. When permeability is infinity, okay, when permeability of the core is infinity, then what will happen? So magnetizing current is equal to the zero. Okay, but the flux is present in the transformer. That means without any magnetizing current, okay, when permeability is infinity, the without any magnetizing flux is present in the transformer, but practically it is not possible. So these are one of the characteristics. And second one is this losses, okay, iron losses of the transformer, okay, this iron loss is equal to the zero, and our losses, iron loss and copper losses, both are the is equal to the zero. And third one is a winding resistance of the transformer is equal to the zero, and fourth one, leakage flux is equal to the zero, and there is no leakage, there is no saturation effect and hysteresis effect in the transformer. These are the basic characteristics of ideal transformer. But in this question, indirectly mentioned the infinity core reluctance. Okay, so we know flux is equal to mmf by the reluctance, right? So when in this case, suppose when the reluctance of the core is a infinity, reluctance of the core is equal to infinity value. Now what will happen? Flux is equal to the zero. So this flux is present in the ideal transformer. Flux can't be zero. So that means this characteristics is the wrong. And next, coming to the large magnetizing current. The large magnetizing current means ideal cases magnetizing current is equal to, okay, magnetizing current is equal to the zero. That's why we need to choose the material which has the infinity value of permeability of the transformer core. So that's why this is also wrong answer. Now next one, zero core flux. Okay, flux is present in the ideal transformer, but magnetizing current is equal to the zero. Now zero stored energy. There is no stored energy in the magnetic circuit. So this is the right answer for this question. So option that 2 is the correct for this question. Got it? Now let us solve another question. This question belongs to the concept of eddy currents. Which of the following is correct regarding eddy current losses in the coil? First option A, by making the use of a laminated core, eddy current losses are increased. The eddy current converts useful energy into the heat and waste heat. Eddy current flow in the straight line like wire, complete the circuit path without power loss. Eddy current helps in the generating the electrical energy. Eddy current means power loss in the magnetic core due to temperature rise. Okay, because of finite value of conductivity of the core. So eddy current losses in the sense, eddy current loss converts the useful energy into the heat and waste it. So simply it is nothing but another name of this one is called simply the eddy current, the power loss. Okay, power losses here. So eddy current means circulating current in the core. So this circulating current the produces the circulating current creates some amount of heat and waste heat. So this is known as eddy current power losses. Got it? Okay, this was the end of the discussion of questions of the transformer. Thank you.